Hello and welcome to another video. In this video we're going to be working on partition array for maximum sum. And in the problem you're given an integer array R and you want to partition the array into contiguous subarrays of length at most k. After partitioning, each subarray has the values changed to become the maximum element in that subarray. Return the largest sum of the given array after partitioning. Test cases are guaranteed such that the answer fits into a 32-bit integer. So in this first example, basically the partitions are like this. So this is one partition. The 9 is in a separate partition, and this is in a separate partition. And you could see all the values are transformed, and the sum is 84. And they have this for the second sum. They didn't really tell you like how. But essentially, if you think about it, first of all, like the problem description isn't the best, so that is one thing. But basically, they tell you you can partition it into contiguous chunks, and then anytime you partition into a chunk, that every number in that chunk becomes the maximum number in that chunk. So essentially, it's kind of straightforward what you need to be doing, right? So let's say we have an array. So let's just draw an array. Maybe we can use something like this. So let's just pretend the values in the array are these values. Maybe I can even do this. Perfect. And let's say k equals 3. So essentially, our choices are we can partition the first chunk into one element, or we can do 2 elements, or we can do 3 elements. And it's kind of hard to figure out like what's the best thing. Like obviously, if this was some kind of sorted thing, maybe you could do greedy. Oh, but yeah, you could do greedy actually if you did sort. But the problem is that you can't sort, right? You need contiguous chunks. So we can't sort. These elements can be all over the place. So you can't. There's no like best way of doing it. But we do have a choice, right? Like I said, starting at the beginning, we can split into one element. Like this first chunk has to be one element, or 2, or 3. And think about how long this takes to do. This is pretty easy, right? Like we can just maintain an index of where we're at, and then just try to split at all those locations. So we could like try to split here, and then start over here with a new chunk. We could try to split here, start over here, the new chunk, try to split here, start over here, the new chunk. So it's pretty easy to do in a recursive function. So that's what we're going to do. Since we have choices, we're going to do dp here. So for dp, once again, as always, you need 3 things. So you need state, you need a base case, and recursive case. So let's kind of maybe walk through some recursions of this, essentially. And it's pretty easy, I think. But let's actually fill in all our states. So for our states, all we need is the index. And we can do this in like a really smart way, so all we need is just the index. And then this will easily pass because the array length is only 500. Now the base case is when we're out of bounds, we have no more chunks left. So no more chunks. What's our sum of that? Just return 0. And the recursive is also, like I was saying, just recurse at every chunk. And so the main thing is, how do we do these chunks efficiently? Like let's say k is like 5. So how do we like recurse here, get the sum, recurse here, get the sum, recurse here, get the sum, and so on. Like, right? So it's pretty easy. We can just maintain a variable of our elements we've seen, and we'll just store the biggest one we've seen, because the biggest element, like every element in the chunk transforms into the biggest element. So let's kind of walk through that for maybe k equals 5 for like one chunk, how this would work. So k equals 5. So essentially we start at index 0, and we say, okay, well, what's the element here? So it's 0. So our current, let's have a current, it's gonna be 0. And what's our recursive case? It's gonna be pretty easy, right? We just take the length of our current array, our current chunk, which is just this one chunk. And that's pretty easy to figure out, right? Based on like whatever index, we're just gonna loop essentially from here to the last element we can have in our chunk. So if k can have 5 chunks, it will be up to this element. So we loop up to here, we'll maintain like the biggest element we've seen, and then the sum of the chunk is just the biggest element we've seen times the length of the chunk. And this is very easy, right? Because we're just incrementing the index one at a time, and the biggest element we've seen, we can also increment in O of 1. So we can calculate the sum of the chunk in O of 1. We can just keep track of the biggest element we've seen in O of 1. So our biggest element we've seen is going to be 0. And then we will say, okay, well, so what's the sum of this chunk? So the sum of this chunk is just 0, because it's 0 times 1. plus, what's the recursive case here? So the recursive case is also really easy. We'll just recurse to the start of the next chunk. So in this case, we'll recurse to index 1, right? Then we move this forward. So let's take this actually and maybe move it like this. And here we go. So now we move here. Now our chunk is this whole thing. We're going to try this chunk next. What's our biggest element we've seen? So now it's going to be 1. What's our sum of the chunk? So our sum of the chunk is the biggest element we've seen times the length of the chunk. So that's 1 times 2. So it's going to be 2 plus dp of going to the next place. So if we say our chunk is length 2, then we're going to recurse over here. Then we try the next chunk. So maybe we'll try to have a chunk like this, right? Like we might have a split like this. And what's the current element? This is going to be 2. And what's the sum of this whole chunk? It's going to be the length of the chunk, which is 3, times the biggest element, which is 2, so that's going to be 6. So this will be 6. It's going to be 6 plus dp of 3, right? That's going to be the next index we go to. And so you basically just keep doing this. You keep traversing the current chunk you're on, keep track of the biggest element, and just keep track of like how long your chunk is, get a sum, and then recurse down to the next index because that's going to be the start of your next chunk. And you make sure you don't go out of bounds, right? So let's say we started here and we try to get a chunk of length 5. We want to make sure like we don't recurse over here. Like we can't have like more elements in the chunk. So for the right bound of the chunk, just make sure it's actually an active element in the array. That's pretty much all you need to do. So recursive case, recurse at every chunk. And then the result here is going to be the sum of the current chunk plus dp of the next index. And that's basically it. So kind of easy DP problem, so we can code it up. So we're going to get a variable for the length of the array. And then for those of you who haven't seen before, so you can make a cache, or you can just write @cache in Python. It's a decorator that will cache things for you. So we're going to use that. So we're going to have a DP function, just going to use an index. So if we're out of bounds, that means we have no more chunks. So if chunk is A, we can just return 0 here because we have nothing left. So let's actually tab this. Now we'll have our result variable, we'll initialize to 0. We'll have our current max, we'll initialize that to 0. Now essentially we can loop from our current index to our current index plus k. So if our current index is 0 and k is 3, we can loop from 0 to 2 essentially, including 2. So that's what we're going to do. So we're going to do 0 plus k because this will be 0 to 3, but in Python, the right side is the last element is not inclusive, so it'll loop from 0 to 2. And we need to make sure that we're not out of bounds, right? Like what if our array is only length 1? So we will just minimize that with the length of the array. So you can just write for j in range starts at I, minimum of the length of the array and I plus k, just to make sure we're not out of bounds. So if we are out of bounds, we'll stop. Or you could just like check in here if you're out of bounds in the loop, and if you're out of bounds, just break or something. That's fine too. So current max equals maximum of our current element and our old current max. And then when we check our result, so we're going to update our result to be the maximum of the old result plus, or not plus, old result and current max times the length of our current chunk. So the length of our current chunk is j minus I plus 1, kind of like a sliding window. So for example, let's say we're on index 2. We start at index 0. That means we have elements from 0, 1, 2, so 3 elements. So it'll be 2 minus 0 plus 1. So this is going to be the sum of our current chunk plus the dp over recurrence relation, which is just going to be the index right after j. So j is the end of our current chunk, and j plus 1 is the start of the next one. And we just return result here and return dp starting at index 0 for our first chunk. And yeah, pretty much it. So a pretty easy dp function. Apparently screwed this up. Oh, this should be I. So there we go. Yeah, pretty easy dp function. They did have kind of a bad problem description, but yeah. As far as space optimizing, you can space optimize. It's going to be a little bit tricky, and I'm not going to do that here. And you should be able to see that. Notice that when we're recursing anywhere from basically, like if we're starting at index I, we will recurse from any point from I plus 1 to I plus k. So you can actually, well actually would that even be space optimized? Yeah, it would be space optimized. So basically what would happen is instead of I believe, you would store k elements. So our dimension would get reduced from I to k. But in this problem, k can be up to the array length, so it's not actually going to reduce it in theory, but in practice it will, right? If the array is like 500 elements, then we can reduce it down to whatever k is. If k is like 10, we can store 10. If you want to do that, you can do that. It's going to be a tough optimization, and I'm not going to do that here because it's not going to help that much. And yeah, so let's just let's go through the runtime here. So essentially what we're doing here is we have every single starting index, so that's I, or we can call this like n, and in every single DP function, we are basically looping from wherever we are to the length of a chunk, and the length of the chunk is k here. So this is going to be n times k, because the inner array loops through k elements, and the outer array goes through every single element in the array, or the outer DP. And the space is going to be O of n, right? Because we have this cache that can start at every index. So, yeah. So yeah, kind of an easy one. Definitely one you should be able to do on an interview if you get asked. So, if this video was helpful as always, please like it and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.